All righty. Well, as the slide says there, let's go to a quick intermission. Give our next presenters the final 5 minutes or so to get ready. As you can see on the screen, part two starts at 2 p.m. So I will see you all in about 6 minutes, and we'll get going. Thanks for being here, and much more to come. All right, well, good afternoon again, and welcome back to part two of International Day of Light here, where we are celebrating together science and the art of light. I'm your MC, Zach Yentzer here, and I'm honored to be a part of what I think is an incredible initiative to storytell what we are good at, to know what we're good at in this community, to storytell it. And certainly optics and photonics and our experience there is something that makes this community great. It's the science and the engineering of light used everywhere, every day. And Arizona is indeed known worldwide as Optics Valley. Our state is home to world-class businesses and institutions with decades of leadership and innovation in optics, photonics, and astronomy. And throughout the day, you'll get to see and hear from many of those, and many of those are supporting this great event today. Today, you'll find out here in the upcoming few minutes for yourself from both college students and a top scientist who takes images of asteroids and other planets. Before we move there, just want to thank again our great sponsors, our presenting sponsors, the Flandreau Science Center and Planetarium, Optics Valley, part of the Arizona Technology Council, SPIE, the International Society for Optics and Photonics. Also want to thank our gold sponsors at this time, the University of Arizona Bio5 Institute, Edmund Optics, Leonardo, PI, Physic Instrumente, Viavi, and also at this time, want to thank our silver sponsors, AGM on this slide, Arizona Commerce Authority, Blue Canoe Marketing, Pima Community College, Tipping Point, and Wyant College of Optical Sciences. At this time, let's take flight, strap in to visit local optics and photonics leaders, learn what they do and how their work impacts the future. So take a look.
Welcome to the Optics Valley 2021 celebration of the International Day of Light. We're your hosts for a tour of some of the optics and photonics companies located right here in Southern Arizona. I'm Olivia Fehlberg. I'm an optical and optomechanical design engineer with Edmund Optics located in one of our Tucson facilities. For my job, I get to design optical components and assemblies that go into all sorts of markets, ranging from factory automation to laser manufacturing, medical diagnostics to communications and more.
Hi, and I'm Lucas Gruber, responsible for business development in medical, scientific, and industrial markets at Leonardo Electronics. In my role, I'm working with a wide range of international customers exploring how high-powered diode lasers can help them create new products and advance research in science. Olivia and I had the opportunity to talk to representatives from several outstanding optics and photonics companies in town. We're going to show you around and let them tell us what they do, why or how they landed in Tucson, as well as how they see the work that they do affecting the future.
We are so looking forward to giving you a glimpse into our local optics and photonics industry and all the opportunities it has to offer.
So my name is Robert Walker, and I am Vice President of Sales and Marketing at Leonardo Electronics US. And essentially my responsibilities are business development for the laser diode business here in Tucson, Arizona. We make laser diodes, so we make laser products for a range of markets and applications. In terms of market space, we make laser diodes for advanced targeting lasers. So these are lasers that are used to identify targets for smart munitions, for example. We make products for medical applications. So lasers are used in in many different applications, and we focus primarily on aesthetic laser applications, and the most prominent of those is laser hair removal. So our lasers are used to remove hair from people's bodies where they don't want hair. We make lasers for material processing, so the fabrication of materials, cutting and welding. We also make lasers for scientific applications, so very high energy lasers, petawatt class lasers.
I'm the CEO, President, and founder of Advanced Photonics. Yeah, we build fiber lasers. Basically, you try to utilize the specialty glass and the fiber itself. So our products is fiber lasers, fiber amplifiers, but inside always have a piece of specialty gain fiber inside. So in terms of market-wise, we started as SBI company, and we get into scientific market. Nowadays, we really try to focus on industrial applications.
My name is Nasser Pegambarian. Thanks, Lucas, for making this happen. I'm the CEO of NP Photonics. I'm also a professor at the University of Arizona College of Optical Sciences. So at NP Photonics, we build lasers, and these are specific lasers which are called fiber lasers, which means that inside the laser, there's a piece of fiber that is generating the light. These applications range from defense and security to all the way to medical lasers that are used in surgery and medical field, all the way to communication and sensing.
My name is Greg Quarles, and I am the CEO and president at Applied Energetics. So our company primarily focuses on ultra-short pulse lasers, as well as high voltage and the direction of light and voltage together in the form of a directed energy, laser-guided energy concept. And our primary markets are 8 government agencies, U.S. Department of Defense, as well as a few manufacturing areas, dual-use applications in the additive and subtractive manufacturing areas, as well as manufacturing of components using ultra-short pulse optical sources in the biomedical and medical device applications.
So my name is Katie Schwartz, and I am a design engineering manager at Edmund Optics in our Tucson office. And so actually for the past 10 years, I've done optical and optomechanical design, but recently I've moved into a management position. And so now I oversee some of our design group, and I help to make sure we have the right resources to get design work done for the company. So Edmund Optics is a global manufacturing company of optical components and optical subassemblies. So we manufacture, we do our own design, and we help customers go from prototypes to production level products. So optics is a bit of what we call an enabling industry, in that it is in a lot of other markets. And so we basically sell to other businesses and other markets outside of optics to help enable products that you as a consumer or a customer would buy off the shelf.
So my name is Robert Schroeder, and I'm Vice President of Operations for Optical Support. My role, in addition to kind of the day-to-day operations of the company, are primarily engineering, contracts, and customer management, and new business development. So optical support, as the name may imply, is an optical engineering services firm. We specialize in the design, fabrication, assembly, and test of optical subsystems for markets like semiconductor, aerospace and defense, biomedical, commercial sensing. So one of the bigger systems that we've done to date was a large interferometer system that was used to test silicon wafers during deposition of computer chips or electronics chips. Mm-hmm. That system was about 7 feet tall. It weighed about 1,800 pounds.
Wow.
And those systems are now in use in chip manufacturing plants around the world. The largest of those custom lenses that we built was a 25 element lens that weighed over 225 pounds.
So just to give the people at home a little frame of reference, your your camera lens for your Canon or your Nikon tends to have maybe 7 to 9 elements, and they don't weigh that much nearly at all. So that's a pretty massive lens.
Hi, Lucas. Thank you very much for the opportunity to speak to you today. My name is Kate Medicus. I am the CEO of Rudo Cardinal. Rudo Cardinal is a custom firm. So what we do is we take any customer's needs in terms of solving an optical challenge. One of the things that we're working on right now is a camera for a satellite repair mission. So that's an application where we talk about very challenging environments. You've got very cold and very hot environments in space. So right now we're building an instrument that uses light to measure a biological sample, and that we can detect certain viruses or certain bacteria in that biological sample, and that will greatly enable speed in testing of those biological samples. And we understand how important that might be right now. What markets we touch? So we touched on some of the space exploration and the scientific work study that we do. Biomedical instrumentation is something that we also do. Defense work, helping our warfighters and our country in that regard, is work that we do also. We also have touched on commercial applications. We've built a system for Hollywood for a better camera so that we can get nice movies that we do like to see. So we're in a wide range of industries, anywhere that somebody needs light to do something.
All righty, incredible to see who is here in our community. Again, I think I'll just keep saying it throughout today. The key is to know what we're good at. We're great at optics here and how to tell that story. And so it's exciting for me that we're getting to hear from so many of these companies who are doing great work. Some maybe we know really well, and some that we've just discovered today. And I hope for some of us, we've discovered today, wow, Tucson is an incredible place for optics. I want to turn it over to our guide for the next few minutes now, Olivia Fehlberg. We got to meet her on the video, and there she is today. Is a design engineer, Olivia is, with Edmund Optics. And Olivia, the show is yours. Thanks for guiding us through the next few minutes.
Olivia, we can't hear you.
Can you hear me now?
Sounds good.
Okay. Thanks, Zach, so much for the introduction. I'm very excited for our next few presentations. Our first one is going to be a demonstration by one of Wyant College of Optical Sciences' own undergraduates, Alyssa Baller. She's going to be showing us all about total internal reflection, which you've heard a little bit about reflection already today, in a waterfall.
And so if you want to follow along at home, and don't forget this is recorded, so you can always try this later, you'll need a laser pointer, an empty gallon container, some milk droplets, a clear baking pan, so maybe that casserole dish that your parents like to use, and then a water drain of some sort, like a sink or a bathtub works really great. If you have any questions, go ahead and drop them in the Q&A during the presentation. And we have a couple of very kind students, Miriam Baker and Trenton Brendel, who will be answering those questions along the way.
Hi everyone, my name is Alyssa and welcome to Laser Fun Day 2021. So today I'm going to be talking a little bit about total internal reflection. So what the heck is total internal reflection? Let's just break that up. Total internal reflection, or TIR. There we go. TIR. Total internal reflection. Now, what do those three mean to you? So when I say total, what do you think of? What other word? What's a synonym for total? I think of everything, right? So we're going to say everything. What about internal? If I were to say that there's internal bleeding, that's not good, right? But that means there's bleeding inside of you, right? Or inside of someone. Not the best example, but internal means inside. Okay, what about reflection? When I say reflection, what do you think of? I think of mirrors, right? So I think of, if I look in a mirror in the morning, fix my hair, before I go to school, I see myself, right? So something is gonna be coming back at me, right? So we're gonna say back at you, back, okay? So putting that together, total internal reflection means that everything inside comes back or stays inside, for example. So what does that mean? Why am I telling you about this, you might ask? What are some applications of this? So we're going to talk about how this actually works with some pictures. So first, let's talk about light, right? Optics, we got to talk about light here. So does anyone know how fast light moves? Do you think I could run faster than it? I wish I could run faster than it. So light is actually the fastest moving thing. So it moves at just this wild speed, this speed that I can't even comprehend. It moves at, take a guess when I'm going to stop putting zeros. So maybe 300. These units are going to be in meters per second. Okay? So like a meter is, yay-ish big. Meter stick, yard stick, about that. So do we think it moves at 300 meters per second? That'd be pretty quick. Doesn't. We're going to add some more zeros. 300,000 meters per second? Not quite. What about 300 million meters per second? How does that sound? That sounds huge, right? Just for an idea, I just did a quick Google search. The circumference of the Earth, so the distance all around the Earth, is actually 40 million meters. This is Earth. This is light. So what the heck does that mean? That means light can go around the Earth about seven-ish times in a second. That's how fast light moves in air. Why do I mention in air? Well, light actually is going to move at a different speed in something, for example, like water or glass, for example. That speed of light is actually going to decrease if it's not in the perfect material. So the perfect material is outer space, right? Where it's just a vacuum. Air is pretty close to that though. But then we have other materials, like I just said, water, where that light is actually going to be moving at a different speed than it is above, like in the air. So this is where total internal reflection comes into play. So we're gonna draw this out, and this example is going to be for water, right? So for a pool. So we're just gonna draw this line here. We're gonna call this your pool's surface, okay? So up here we have air, down here we have water, okay? So what happens whenever you have, let's say you're leaning at the bottom of the pool, right? You blow out your breath, you're sitting there and you're looking up. If you were to shine a light just up into the water, what's gonna happen? What do you think is gonna happen? Do you think it's gonna shine up to the sun? Do you think it's gonna come back and reflect back down? Do you think it's gonna like go straight, it's gonna bend? What do you think it's gonna do? So there's some other questions we have to ask before answering that. We have to know what the angle is that we're actually pointing our little laser or our light at underwater, hypothetically, right? So we're gonna just draw 3 different examples, okay? So we're gonna call this straight up. We're gonna call this straight up for 1, straight up for 2, and straight up for 3. Okay, just 3 different examples. We'll put a little break in here. Okay, so let's talk about the first thing that can happen. First thing that can happen is, you're sitting down here and you kind of shine it just at like a small angle, right? So small angle meaning just like that. Oh, sorry. Just so it goes through here. A nice straight line that goes there, okay? Draw a nice arrow. Our blues for our water. So we're gonna just call this angle here, angle A, okay? So we have angle A. So what's gonna happen there? That, if we shine it at that smaller angle, the light is actually going to come out, right? But it's actually gonna be bent a little bit. So you can see it's not just going at the same angle, but it's gonna be bent. So we're gonna call this A1, angle A1, okay? So does this happen all the time? If I shine my light underwater from any angle, is this gonna happen? Not quite. There's something called a critical angle. What the heck is a critical angle, Alyssa? A critical angle is the angle where if I were to shine it up at this certain angle, then the light is actually going to kind of stay within the water, is what we're gonna kind of call it. So we're gonna say that that angle is just about here, okay? Okay, so it's going here. This is our angle B. Okay, so when it goes through angle B, it's actually going to just go right along the water here. Okay, so this is what we call the critical angle. Alrighty, and so, okay, that's kind of cool. If you have it at this perfect angle, it'll just kind of stay there, won't necessarily go up or go down. So, can anyone guess what the last case is going to be? We have a case that's going up, we have a case that's kind of staying on the water. So, a third case is going to be when it reflects back. So, let's go ahead and draw that. As you can guess, we're going to be having a little bit bigger angle, like that, we're going to say. This is going to be angle C, okay? So, we have angle C going up here. That angle is going to reflect back. It's not necessarily going to reflect back this way, it's going to come back here. Okay, so this is going to be, we're going to call it C1. Okay, so this is what we call total internal reflection, or TIR. Great, thank you for sitting through all that with me. Now that we have that information, we can talk about what cool things come from this. So I'm gonna go ahead and flip around and do some demos. All right, so stay tuned. All right, everyone, I'm back. So now that we've gone through the math part of total internal reflection, we're going to go through a few examples. So what are some examples? How are we going to go about this? Well, we're going to start with our handy dandy laser pointer. As you can see here, I just have a green one. Hopefully you can see that. So if you guys have your laser pointers at home, we'll be able to find a few things that you can use those for. But for now, I'm going to use some examples that I have here in the lab, here in the optics building. So we're going to go and start with this acrylic rod. So why are we starting with this acrylic rod? We just did this example using water, right? We used water and air. So now we're going to go ahead and transfer that. And instead of using water, we're going to use this glass. And the property works similar. The total internal reflection works similar. The light just moves at a different speed through glass than it does at water. It actually moves slower through glass than it does water, and even slower compared to air. So we're going to go ahead and look at this rod. So it's just clear, right? What do you think is going to happen? If I were to shine, I know you can't see, but if I were to shine a light through the window, for example, the neighbors would probably be able to see it, right? Or you'd be able to see it in your backyard. So if I shine it through this, you would think that it's going to be able to go through it, right? Well, yes, to some degree, but let's think about what we just did. Total internal reflection. What do we think that's going to look like in this rod? Why do you think I'm showing you? Let's try it. So first I'm going to just go ahead and point it straight through. So I'm just going to go like this and point it through. And as you can see, the light is coming out here on the other side, right? It's going straight through, and I just have a pretty flat angle. So what now? How, is that total internal reflection? Not quite. Total internal reflection is going to occur when I bend that light, right? When I'm changing that angle. So I'm going to go ahead and change this angle. We're going to start with flat-ish again. I'm going to bend it. I'm going to give it some angle. And as you can hopefully see, you can see a bend. Oops, we're getting a little distracted here. Okay, you can see the bend in the light. For me, it's right around here. Okay, just depending on how I'm holding it and such, right? So what is happening? This light is still coming out, right? So it's still going through, but hopefully you can see that there's actually some points where the light changes direction. That is what this total internal reflection is. So it's hitting it right here. This would be the example of air and water for us, right? And it's hitting this angle, and then it's reflecting back down. So you can see if I do it more and more, then you can see there's more and more. Those angles are going to become more steep. And so this is what total internal reflection is. This is just an example of it. You can go down, you can go sideways, right? All around. It's kind of cool, right? So what is this used for? This can actually be used in something called fiber optics communication systems. If you know what that is so great. I did not know what fiber optical communication systems was until I started optics. So I actually found out that there are these long fibers, so similar idea to this, long tubes, for example, that there is light going through it, wavelength going through it, that is carrying information. And what is happening along these fibers is this total internal reflection. So light is just bouncing back and forth through it, and it's going long distances. So from my apartment to, the university, that's long to me, right? But even longer than that. These fiber optical communication systems are actually laid across the ocean, which is just kind of crazy to me. So you can actually have them carrying information, transmitting information across the ocean. And does anyone know why we're doing that? Why would we be doing that instead of the classic wires that we've been using forever? What's special about light? We talked about at the very beginning. Light travels fast, right? So when it's traveling through these fibers, it's traveling at 300 million meters per second, right? And so this information can get to where we want it to be faster. So that's why we're using fiber optics. Some fun examples of other fiber optics were like these things. I don't know if you guys had these as kids. If not, these were just some toys that we had as kids. So here's just one where it's just a light. I turn on the light, you can see it, and that light actually travels through these little fibers, and through total internal reflection, you can see them, at the top. This is just a little bit more a bigger example so you can see it's going through specifically the ones where that laser is pointed to. So as I change my direction of my laser, different ones are going to get lit up. And then here's just an example, kind of combining those two. So it's kind of got the fun ending over here, but this is more of an idea of those fiber optics cables. So the idea is that it doesn't need to be straight. The cable does not need to be straight because it's just dependent on the angle, right? This angle that the light is hitting between the two surfaces, between the air and the acrylic or the water or whatever the surface is. So I can actually hold this in, a circular fashion, and I can go ahead and shine this light through, and we can see that it comes out the other end. And this is still because of total internal reflection. It's just bending all over, but that light is able to travel. So, when it's going across the ocean, if it's not perfect, that's okay. That light can still get through. So that's just a few examples of how we can use total internal reflection in our world around us. So I hope you guys learned something today, a little something about total internal reflection. And I hope that you enjoy all the other videos and hopefully Laser Fun Day as well. Thank you for listening, and y'all have a great night.
Great. Thank you to Alyssa for recording that as part of the Laser Fun Day and for sharing that with us today for the International Day of Light. We have a second demonstration also from a student at the Wyant College of Optical Sciences. Christian Pluchar, I believe, is a doctoral candidate and is going to be showing us a demonstration on the speed of light, which was one of the things that Alyssa had mentioned in the beginning of how fast the speed of light is, and kind of how you can see this at home in your very own microwave. So your at-home materials for this one would be a microwave, a candy bar or a fruit by the foot, and a ruler. And same thing before, if you have any questions, please feel free to type them in the Q&A. We've got some lovely students here who are available to answer those as we go along.
Hi everyone, my name is Christian, and today we're going to perform a cool experiment that you can do at home to measure the speed of light. All you need is a microwave, ruler, and a chocolate bar or your favorite candy, like I've got here. Measuring the speed of light has fascinated some of the smartest scientists for centuries. If you've ever seen a thunderstorm in the summer, you can get a feel for just how fast light is. Looking at a bolt of lightning off in the distance, you can see the light before you can hear the thunder. Sound is also very fast, but light is that much faster. Because light travels so fast, it's really good at sending information to other people. One reason you can see and hear me now, or a video call with your friends and family, is because light moves so fast, and it gets to places almost instantly. Even crossing large distances, light seems to move from one point to another almost instantaneously. For light to go from the Earth to the moon, it takes only 2 seconds, while the astronauts that went to the moon took a few days to get there. To understand the experiment that we're going to do, we first need to understand a little bit more about waves. Waves are found everywhere in nature, and light is no exception. It's actually a wave. If you've ever gone to the beach, you're probably pretty familiar with what waves look like, but you might not know that light can also be a wave. It took a long time for people to figure out that light was a wave. We now know that light is made up of electric and magnetic fields. How these electric and magnetic fields interact to create a wave is complicated, but the results are all around us. The light that you see are a result of these types of waves. But there's even a lot of light that you don't see. For example, if you use a cell phone to make a call, it sends a form of light known as radio waves to a phone tower to transmit the information in your phone call. If you've ever seen night vision cameras, they look at another form of light called infrared light to pick up on people's body heat. Even another form of light are called X-rays, and they're used by doctors to image bones and other parts of your body. All of these are forms of light, but the difference between them are that they're waves of different frequencies, or equivalently different wavelengths. So here I have an illustration of what a basic light wave looks like, frozen in a moment in time. The distance between these two peaks is called the wavelength. These peaks move as time progresses, and the rate that they cycle between being fully up to fully down and then back up again is known as the frequency. So a quick illustration of what this would look like is, so we have light at this moment in time, and then a little while later, the same wave of light might look something like this. And so it goes from having big peaks here to a little bit smaller peaks, and then over time these peaks get a little smaller and a little smaller until this is completely flat, and then it starts oscillating back the other way until it gets bigger, and so forth. And so a point here is going to just move completely up and completely down again. And you're probably pretty familiar with what this would look like if you've ever played around with a string that's tied at both ends. Like, say, like a guitar, for example, if you play like a chord that's really low, you might be actually able to see the string move. And it's got these what are called nodes and antinodes at different points along the string. And so, like I said earlier, the wavelength is simply the distance between these two peaks, and the frequency is how fast these peaks go up and down like that. And we usually express the frequency in terms of a quantity called hertz. So hertz just means the number of times this repeats itself per second. So if you have this wave and it goes up and down 2 times in a second, that would be oscillating at 2 hertz. So it's this quantity called, that we talked about earlier, called the wavelength, that defines whether or not you can see a beam of light. For example, if the distance is really long, it might be a radio wave, and your phone or computer could use it to look at websites. If it's really short, it could be an X-ray, but just the right wavelength, and it might be red or blue light, something that you can see. Another important thing is that the wavelength and frequency of a wave are related. This is actually really important to the experiment that we're about to do. The relationship is that the wavelength times the frequency, as I've written here, with W representing the wavelength and F representing the frequency, equals the speed or the velocity of the wave. That's the one equation that you need to know. I promise no more math. So the important thing here is that if you can determine both the wavelength and the frequency of a wave, you can measure how fast it's going. And this is exactly what we're going to do for light. Okay, so now it's time to get your chocolate bar and get near your microwave. So I'm going to come over here to my kitchen. And let's get my camera set up so you can see my microwave. So the important thing to realize about microwaves is that they just emit a form of light, and that light is known as microwave radiation. And this microwave radiation contains enough energy so that it can heat up your food. And so what's convenient is that on the back of your microwave, it's going to be tough to see with my camera, but on the back of your microwave, it lists on the back here, it has a lot of information but it will list the frequency of the wave that your microwave is emitting. So usually it'll be a number followed by the letters capital M, capital H, lowercase z. And this stands for megahertz. So a megahertz is 1 million hertz. So that means 1 million cycles per second. So looking at the back of my microwave, it has listed a value of 2,450 megahertz, which means that the waves inside this microwave oscillate at 2,450 million times per second, which is over 1 billion times per second, which is really fast. What's even crazier is that the microwaves are relatively low frequency, and that the light that we see oscillates thousands of times faster than this. Okay, so now that we have the frequency, now's the fun part to measure the wavelength. The first thing that we need to do is actually take out this rotating plate in your microwave. And what this does is it rotates your food so that the energy distribution from the energy of the waves that the microwave is giving off to your food is evenly distributed throughout your food. So it doesn't like have super hot spots and stuff. But we're actually going to use this to our advantage here in a second. So we want to take out the plate and like this little wheel and just set it aside for a second. So your microwave should just have this, and it will have this like little rotating thing at the bottom. And there's a couple, you might have to be a little clever here to, if you place something on top of that, it'll still rotate around like a plate. So what I've done is I've placed my chocolate bar on top of a plate and flipped it upside down so that this wheel is going to rotate underneath it and it won't move the chocolate bar. So next what we're going to do is take the chocolate bar on the plate and set it in the microwave. And the orientation that you put the chocolate bar here is actually kind of important. So you'll see on this side of the microwave and this side of the microwave, there are these little holes. And that's where the waves are actually emitted from. If you think about this string analogy with waves, there's one end of the string that's tied here and one end of the string that's tied here. And microwaves are emitted like this. So what you want to do is orient your chocolate bar so that they're kind of in line with these holes. Okay, so now that we've done that, close up the microwave. And I've found this works with my microwave pretty well for about 30 seconds, but it's going to depend on the power of your microwave and things like what sort of candy you're using or how hot it is. Like if your chocolate bar is already kind of melting because it's already hot here in Arizona, then you might need a little bit less time. So I'm going to start my microwave for 30 seconds. And while we do that, I'm going to talk about what's going to happen here. So back to my whiteboard. So let me redraw this wave for you. Just do a little erasing. Give us a little room. Okay. So in this box, okay, there's the chocolate bar. We'll look at it in a second. In this box, I'm going to draw another wave. And we're going to talk about the energy of this wave and where the energy is located. And if this is kind of the like zero spot where this point and this point aren't moving, the points that have the most energy are going to be a point like this, or a point like this, or a point like this. And this is because this is where the wave is moving the most. it changes the most in time. And so if you've ever like played around with a string that's attached at both ends again, you can think about like this is where the string moves the most. And so that has the most velocity, and therefore that has the most energy. Or if you've been surfing, you know that you go the fastest when you get close to the crest of the wave. That's because the wave has the most energy there. Versus the flat part in between the waves, you won't go very fast, or it won't push you very much on the surfboard because there's no energy there. And so this is the spot where the microwave is going to heat up our food the most, because there's the most energy being absorbed by the chocolate bar, the candy bar, whatever you put in your microwave. And so let's go take a look now at the chocolate bar to see what happened. I'm going to bring also tape measure along. So here we go. So have the chocolate bar, and you can see that in two spots here, it's melted. And so those correspond to the spots that the wave has these peaks in it, and the most energy, and therefore transferred the most heat to the chocolate bar. So the distance between these melted spots, that actually corresponds to the wavelength of the light that's being emitted by the microwave. And so we can take our tape measure and measure the distance between these spots, and that will tell you what the wavelength of the microwave is. So I'm going to take the tape measure, come over here. There's going to be like a kind of a wider area that these are melted in, so you want to take kind of the center, or alternatively you can go, and if it's more clear where the unmelted parts are, like for example this is very clearly not melted here, and there's nothing that's left on my finger, but this is very melted here. You get a lot of melty chocolate. So what you can do is you can measure either between two unmelted parts or two melted parts. So I'm going to take the tape measure, and the distance between the center of the melted parts is about 10 centimeters. There's the 10 over there. Okay, so last thing we have to do is we have to do a little math. So we now have both the wavelength, which we just measured to be 10 centimeters, and we also have the frequency of our wave, which we just got from the back of the microwave. So we've got the wavelength and the frequency here, so we can determine the velocity. So now you can go, if you've got a calculator handy, I've just got one on my computer, and so I'm going to plug in. So we want to be in the units of meters, so 10 centimeters equals 0.1 meters. So 0.1 meters times 2,450 megahertz. So we need to multiply 2,450 times 1 million. So add 6 zeros. And this gets us a value of 245 million meters per second. So this is really fast. And it's actually pretty close to the consensus value for the speed of light, which is like the value that most scientists use is around 300 million meters per second. So for only using a microwave, a chocolate bar, and a ruler, we're able to measure the light, speed of light to fairly good accuracy. So I hope you enjoyed this little demo, and now you get to reward yourself with eating your your chocolate bar that you use to make the measurement.
Great. Thanks to Christian for that wonderful demonstration, and I look forward to melting my own chocolate bar to measure the speed of light based on my microwave. So we've learned a lot about the different parts of light. So why don't we now learn a little bit about what we can do with that light? So we have Dr. Bashar Rizk, who works as an applied physicist in a university research and development setting for 40 years. 35 of those have been at the University of Arizona own Lunar and Planetary Laboratory, working on spacecraft and remote sensing systems. And Dr. Bashar is going to talk about how we can take images of the surface of an asteroid. So take it away, Dr. Bashar.
Thank you so much, Olivia. How am I coming in?
Just fine.
Can you see my screen?
Yes, I can.
Right, great. I'm going to go into presentation mode then. And I should be in presentation mode. Everything cool? You there?
Yep, looks good.
Okay, terrific. So you guys, my name is Bashar Rizk, as Olivia said. Thank you very much for that intro. It's an honor and a pleasure to be here. I was invited by Flandreau Planetarium 36 years ago when I got to this place in 1985. The one thing that convinced me to stay was that my building, which is Lunar and Planetary Laboratory, was right next door to Flandreau. And since I've grown up loving the visits to planetariums throughout my life, I was just said, this is the place for me. So I'm going to talk today about the Osiris-Rex mission and how we've learned things through light. And light, if there's a theme to this presentation, it's that light reveals reality. And that picture of reality that reveals is often complex, and light's able to look at that complexity and convey it. We ourselves do not as good a job in understanding that reality. So let's go immediately to the first image. And the first image, so basically what I tried to do today was pick several images from the mission that were my favorites and I thought could convey this whole story that we're trying to tell today as part of the International Day of Light. I failed miserably. I was not able to pick just a few images. I picked more than 20. Unfortunately, that's not going to fit into today's presentation time. So I cut them and cut them. I still had too many this morning. So I went through a final round of cutting them. But the one that made the cut through all of those was this image. This is a selfie, if you will, that the spacecraft took when we flew by the Earth after being in space for a year. We looked back and snapped this selfie of the Earth-Moon system. This is an actual image of both the Earth and the Moon. I am going to show you the conditions under which we took that image. So I'm flashing up here an inset that has the picture of the spacecraft upside down, looking at the Earth-Moon system in the confines of one frame or one image. I hope you can see that. So the Earth is here as a green circle and the Moon here up in the corner as a yellow circle. And I'm going to take that off so you can see that's what we took, right? We were 5 million kilometers away from the Earth-Moon system, or 3 million miles away when we took the image. The Earth-Moon system itself, if we were to view it broadside, would be something like 250,000 miles wide. So if you look at that picture of the Earth and the Moon, I want you to hold that in your heads, because when we go to the next slide, you're going to see something that is going to look a lot more crowded than that, but deceptively so. So this is a picture of the solar system as we know it, at least the inner part. So on the right, it's as if you're viewing it from the top looking down. On the right, you see the sun at the center, this yellow blob. These 4 planets are the 4 terrestrial planets, starting with Mercury, moving out to Venus, then the Earth. The Earth is right at the edge of this kind of reddish region to this blackish or pinkish region. And then as you get to Mars here, we start to approach this greenish region. And then out here at Jupiter here on the left. So these are the 5 planets closest to the sun. And these green blobs here are the asteroids. And in 2015, when this image was made, we only knew about 700,000 asteroids. Now we're past 1 million and still counting. 25,000 of those 1 million asteroids are near-Earth asteroids. They're the ones that are colored red in this image on the right. On the left, we have a kind of movie that shows you the same thing viewed from a different angle. Now, this image is one of my very favorite planetary images. It was constructed by a Scottish gamer named Scott Manley, but it is a total lie. And why is it a lie? Well, because you see these asteroids piled one on top of the other like they're touching. But you have to remember that the average separation between asteroids is 4 to 5 Earth-Moon distances. So if I show that picture of the Earth and Moon again, broadside, multiply that by 5, and that's the average amount of space that's between these green dots here that are piled one on top of the other. So that's our first lesson. Space is vast, and that is the thing that we are launched our spacecraft into. We are trying to represent reality with this beautiful image. Real reality resists our ability to represent it. And so let's push on and try to look at other examples of this. We arrived at the asteroid Bennu in December 2018. So I hope you brought your Anaglyph glasses. Anaglyph glasses are red-blue glasses, and I'm gonna show you here a picture of them. Let me see if I stop sharing here. You look, I have in my hand here an example of red-blue glasses, and I'm gonna start sharing again. And if you put them on here, you should see the right-hand side of this image, which is moving again now, which is a picture of the asteroid when we first got there at very close to 0-degree phase angle. What's phase angle? That's the angle at the asteroid surface between the sun and ourselves. So it means that when we took the image on the right, which I'm going to start up again, the sun was directly behind us. Now, if you don't have Anaglyph glasses, so let me just quickly say that for the image on the left, we took about 3 or 4 months to get to a place where we were 2 million kilometers away from the asteroid to a place where we were just a couple of kilometers away from the asteroid, where we took the movie on the right. That was a very exciting time as we were watching the asteroid become go from a point source to become a 3D object. Now, if you don't have Anaglyph glasses, I included this free view stereo image of the same asteroid rotation movie on the left. Now, to view this, we have to look at, and this is going to sound simple, but it's not. You have to look at the rightmost image with just your right eye, the leftmost image with just your left eye. Now, you can't do this easily by not interfering, not using other means. But I'm going to show you a picture of one of those means that you could do. So that's me this morning separating this very image. And I used a piece of cardboard, which is the same cardboard that you get at the back of a notepad or something like that. I put it right on the seam between the two images. And it allowed me to look at the left image only with my left eye and at the right image only with my right eye. And if you do that, you'll see a double image. And then you'll take your eye and do whatever you need to do with your eyes to try to bring those double images together into a single image. Once you do, that single image will be in 3 dimensions. So I've given you 2 ways here to look at 3D objects in space with a 3D rotation movie, one on the left with free view stereo, that's just your eyes. On the right, you can use Anaglyph glasses to do the same thing. What we saw when we got to this asteroid was a very rocky surface. Now, let me go here to this flat rotation movie of almost the same thing. The difference here, so there's no Anaglyph glasses or eye adjustment necessary to view this image. What you see here is this image is slightly different. I'm not taking this at 0 degrees phase anymore. The phase angle is something like 30 degrees. In other words, the sun, rather than coming and shining on the asteroid from directly behind me, is shining on the asteroid from the left. So it shows this line of light and dark here on the right, which we call the terminator. Now that's the line separating the bright part of a planetary object like this asteroid from the dark part. So the dark part is in night, the bright part is in daytime. On the seam is this thing called the terminator, which is in half light or twilight. Sometimes we call it on the Earth. That's the time of sunset and sunrise. Why is it important for the asteroid? Well, it turns out when you've got an object as small as Bennu with such a low amount of gravity and you want to orbit it, you can only orbit it stably by following the terminator. In other words, your spacecraft has got to follow this line of light and dark. Now, why does it have to do that? Well, light is not a massless substance. It's got momentum. Well, let me rephrase that. Individual photons are considered to be massless, but despite that, they carry momentum, which means they carry energy and they impart a force to objects like the asteroid and objects like our spacecraft. So the gravity is so low on this object, it's pulling us in toward the center of the asteroid. Solar radiation pressure is pushing us outward from the sun. Those two forces balance ideally by following the terminator. So by following the terminator, we're actually held stably in orbit by solar radiation pressure, which is kind of a bizarre concept, which is not true of the vast majority of spacecraft missions, which orbit objects that are very, very massive, like Mars or the Moon or Jupiter. Not us. We tried to make an orbit and successfully contained orbit around this object right here. So sunlight has momentum and force. Force turns out to be the derivative of momentum. What's a derivative? Well, that's if you're moving along on the highway and with a certain speed, and you ask yourself at any time, knowing if you have an expression that expresses where you are with time, say going from Tucson to Phoenix, and you ask yourself how fast you're going, well, the mathematically formal way of getting your speed from your location is called a derivative. And that just points up the need for, as several of the speakers this afternoon have introduced, that we need math to understand the world. Is it a perfect way of understanding the world? No, it's not. It's not even as perfect as these images, which convey way more complexity than the mathematical models that we form. But we can't use these images to get to the asteroid and safely orbit around it without using math. So right there, the tension between math and the pictures that we show and the light that it takes to convey them is very evident. Now, I'm going to go ahead and move on, but I wanted to say one thing before I moved on, which is that why do we need to be stable when we orbit an asteroid? Well, it turns out that when we leave, or when we try to take images of the asteroid, we have to leave that stable orbit and go around to the front. In the orbits that we use to survey this asteroid and create the mosaics like the one I'm showing here, require us to enter an orbit that's not quite stable. We'd like our orbits to last at least 2 weeks, because if the spacecraft goes into safe mode, or what's called safe mode, we want to be able to recover gracefully. So that is a whole complication that we don't normally have to deal with when we're doing day-to-day things in life, but we have to think about when we're operating a robotic spacecraft at a few hundred million miles away from the Earth. All right, so we did leave the orbit and create this beautiful mosaic here. And if you look at, I believe that, yes, if I click on here, we identified a primary and a backup site by which we could collect a sample. And I'm neglecting here to see if I have any questions. And I don't seem to have any questions, so I'm going to push on. But I'm hoping that Olivia will turn off people's mutes. And then if you just want to ask a question, just go ahead and shout it out. I've noticed that we're down to about 30 some participants here this afternoon. So I think that's few enough that we're not going to get chaotic here. If you guys just want to call out your questions, as you have them, which I totally invite and welcome. So we had to pick a primary and backup sample site here. And before we could actually successfully sample them, we would have to get closer to determine whether there's sampleable material there to be picked up. Sampleable material had to be smaller for our sample mechanism, smaller than about an inch or 2 centimeters. Anything bigger, any rock that was an inch or more would not fit through the throat of our sample mechanism. More on that later. I'm going to show you what happened when we actually did the sampling. But in the meantime, we started taking pictures of the asteroid by going closer and closer. And I'm going to show you some of them. So here are the 2 sample sites that we identified as our primary and backup. On the left is the primary, which we codenamed Nightingale. On the right, Osprey, which is our backup site. You can see they're relatively free of boulders and hazardous stuff, but there's still a lot of things that were bigger than 2 centimeters in the frame. So we were a little worried at this point. So we started going closer. And this is our primary. So the next 5 images I'm going to show you are from our primary sample site. Let me just do a quick time check. We're doing good. This is our primary Nightingale sample site here. It's this clear area that I'm indicating with my cursor here. Near it, we see this smoothish boulder, and it's relatively clear of debris. And I'm going to use that to in a good way here in a second. So I'm going to introduce the concept of a witness plate. Now, this is a sample mission where we didn't want a lot of contamination. You cannot completely eliminate contamination when you're constructing something in a terrestrial environment. It's very, very difficult, especially when the different components of that thing that you're constructing, like a spacecraft, come from different places, okay? The spacecraft was assembled in Denver at Lockheed Martin Space Systems. Parts of it were built at the University of Arizona. Parts of it were built at Arizona State. Suppliers of LMS came from all over the United States and even overseas. One of our instruments came from Canada. All these things were shipped to the high bay at Lockheed Martin and assembled there. How do you keep it all clean and pristine? Because we're going to be sampling some of the most pristine material in the solar system when we touch the surface of the asteroid Bennu. Well, you're not going to be able to keep it completely clean. So we adopted a philosophy of maintaining witness plates. Everything that we constructed that went on that spacecraft had riding with it a metal plate that would experience the same contamination that it did. So when the sample comes back to Earth, all those witness plates are going to be archived. And if there's any question as to whether something came from the Earth's own contamination and something came from the asteroid itself, we'll look at the witness plate, which stayed on the Earth and did not go into space. In the same fashion as we look at, or we use witness plates to try to determine if we contaminated our spacecraft, we're going to use this flat rock here to determine, and it's located here, whether there's any small material here at the sample site. So we're going to look at increasingly high resolutions of this flat area. So there's one of them at high recon. Then we're taking images from orbit itself, and you can see the phase angle is very high because we're close to the terminator with a lot of shadows. And then this is low recon, where we're looking practically dead on. The phase angle is much smaller than at orbit, and we can see the surface of this thing at a lot higher resolution. And in fact, if you focus on this blank area here, and you look at the plate scale that you've got in this image on the left, which is basically 33 centimeters or 1 foot across, so not very big at all, you can see particles here that are way smaller than 2 centimeters. So we were able to confirm that in fact there is sampleable material there at the site, and the mission could go ahead. And that's what we ended up doing. We ended up approaching the asteroid. Now, you may have seen this GIF. It was widely circulated. It's a factor of 37 sped up version of the sample acquisition process. So I'm going to move my little icon here and then start it up again. So I compressed 110 seconds to a 3-second GIF. We approach the asteroid surface, And then we ignite a nitrogen bottle that swirls around and agitates the asteroid surface very vigorously, as you can see, almost too well. And in the process, a lot of material gets ingested into our sample head, which is that flat, white carburetor looking thing at the end of the sample arm. So if I look in a different view of this, so this is a little complicated. I'm showing you two views from two different cameras of the sample process. Both have the sample, well, the left one has more of the sample arm in it. The one on the right is a wider view where you can only see the sample arm in shadow most of the time. So if you look in the center, you see the outlines of these two cameras. The smaller one on the left is this orange outline here, and the larger one on the right is this green outline. And I'm just simply going back and forth across the instant of sample acquisition, just so we can try to wrap our heads around this really violent process. And I think I have some questions here. What happens if we contaminate the asteroid? That's a great question. We will contaminate the asteroid. The one thing we can do is try to maintain that contamination to a minimum. We believe there are no living things on the asteroid. So the whole mission, or the mission as a whole, I should say, was considered planetary category 4, I believe, which is not the highest. Category 5 is the highest. That's where you're going to a place where you believe there might be life, like Europa or Mars, or perhaps someday Enceladus. Those places might actually have life, so you are not allowed to bring credibly anything that might contaminate. In other words, living organisms from the Earth. So you resort to things like sterilizing your spacecraft before you leave, making sure that the parts of it that will be exposed to the planetary surface are exposed to the radiation of space, so they'll be sterilized again. And then, if worse comes to worse, and you have to dump something on the surface of the planetary body you're visiting, you blow it up. In other words, you heat it to such a hot temperature that nothing will survive. We didn't have to do any of that because we didn't think that Bennu contained living organisms. Now, that said, we try to minimize the amount of contamination. There's going to be, we're going to be using hydrogen. So the hydrogen is used as a fuel, and thrusters is going to be contaminating the asteroid. And then I got a second question here. Why do you use nitrogen? Because nitrogen is an inert substance, just like a noble gas. So it doesn't react with stuff. It's not very chemically active. And therefore, nitrogen molecules, which is what we use, what we see in our atmosphere and what we use in this bottle, will tend not to contaminate very much. And those are the two questions. Again, just shout them out if you want. I'm happy to ask, and there's a chat here. Okay, good. We're all caught up here. So I'm going to cycle away. So this is just, we're talking about light and complexity. This is a very complex scene that we are trying to untangle at the moment. But before we do that, I got to show you this. Now, this is, again, stereo, anaglyph on the right, free on the left, and you guys know what to do. This is the place we sampled, which is the red circle, just before we hit. So you can see what the surface looks like before we messed it all up. And this is, to me, one of the really exciting images of this asteroid. This is one of the highest resolution images we're going to have, probably the highest, really, that we can get stereo out of this asteroid. And it's, I'm sorry, let me just see what's going on in the chat. Okay, great. We can see what looks like dust coating the surface of these boulders and cobbles at the surface. And that is, let me just check my time here, 3:13, not bad. What we think has happened here on this zero gravity object is that there are a lot of dust balls or dust bunnies or something that's even more elaborate constructions of that nature that we call, this is the term of art, fairy castles. So a fairy castle is something that cannot exist on the Earth because gravity is too high, it collapses. But on a zero gravity object like Bennu, we think it can exist. And in fact, we think it does exist, and that we disturbed what is essentially a fairy castle structure when we so violently expelled the nitrogen from our bottles. Okay, I see another question here. Are there any downsides in messing up the surface? Of course, you don't have a pristine surface to work with anymore. In a minute, I'm going to show you the aftermath of our disturbance. So you see, it's not quite as bad. The thing is, this surface is getting disturbed all the time by micrometeorite impacts. So as we found out when we observed particles being ejected from the surface that we later traced, we think, to meteoroids constantly bombarding the surface of this thing. It was a phenomena that had never before been seen or imaged in planetary work. And it was just, people had suspected it might be possible, but it knocked everyone back on their, it knocked their socks off anyway. Okay, so we get to this sample. We just saw the movie of the sample. Safe distance. Is there a question? I will unmute after my wife finishes her. Okay. We're looking here at an image. We're two images here. The image before is, and I'll get to the questions in just a second. The image before is 2 years ago in 2018, when we looked, we held the sample head very close to our cameras, one of our cameras, and took an image of the pristine sample head. Now, what you're looking at on the left is the underside of this carburetor-like looking sample head, which is about 1 foot wide. And then you can see the gorgeous mechanical makeup of this thing. There is a transparent, you guys can't see it, but there is a transparent mylar flap that covers this entire opening here. And that once you inject nitrogen into the underside of this thing onto the surface of the asteroid and pressurize the cavity within, once it's cupped downward on the surface of the asteroid, then that flap gets swung open and all the sample and the gas enter the inside of this sample head, which most of the space to store sample is in the concentric toroidal bits here. When you do that, all the gas escapes upward out through the sample mechanism, and the sample that you just collected and entrained in your high pressure stream of gas is now lodged safely within your head. We apparently did that like gangbusters here. In fact, we had when we looked at this sample head 2 days after we tagged, we saw so much material inside the head, we think, that the material is escaping through an open mylar flap. And I'm going to show you that in this image right here. So again, it's the same before-after pair. Before 2 years ago, before we even thought about going toward the surface of the asteroid. And this is afterward, where you see stuff crossing in the near field, you know, stuff escaping from the sample head. And you can see what look like a bunch of stones and rocks. Let's see if I got yeah. So I've outlined here where you can see a bunch of pebbles and grains there, just stuffed into the head, stuffed to the gills. And in fact, they are jamming the mylar flap open, and that's why you have all this material escaping. Having seen that, we closed up shop and moved on. So let me just stop here for questions. Would the stones damage the sample head so it can't be used again? Nope, it would not. The thing is tough. It's made out of a strong metal. As you can see, the stuff on Bennu looks like rock, but a lot of it is very friable and very fragmentary. So it's just like not even a close question. What it will do is, once you've ingested a sample from a specific place on Bennu, if you then go back and ingest a sample from a different spot, you've got to worry about the mixing problem. You know, which one is from that side and which one is the other side. We don't really care per se, but I bet future generations will. So this is a picture of the sample head taken by the stow camera after we were just about to stow, and you can see stuff clinging to the bottom surface of this and clinging to the inside cavity of the sample head. And I got another question. Is there a chance too much sample will fall out? Absolutely. We were detecting something like every time we moved the thing to take a new picture, we'd have to move the wrist motor and it would move into a new orientation. We would be losing about 10 to 20 grams. Now, we thought there'd be like 400 to 500. We could estimate from what we could see, we estimated something like 400 to 500 grams. of stuff in there. But if you're losing stuff at 10 to 20 grams a shot and you make too many motions, then it's potential that you could shake it all out. And that's why we decided to close up shop. So here's us closing up shop. Oh, gotta click it through. Come on, I know you can do it. Okay, hold on. Uh-oh, PowerPoint, there we go. I thought for a second PowerPoint was not responding, but it came back to its senses. Can you guys still hear me? Am I still coming through? Hello?
Yeah, you're doing just fine.
Good. Sorry, I had a little bit of a computer event there. So we decided to stow the sample, and this is us stowing the sample. You notice that when we do that on the right, we kind of give it a little tug just to make sure it's locked in there. I thought this was the cutest thing I'd ever seen. So I decided to show a movie of it. Now here we go. This is another Anaglyph stereo, and I'm gonna show Freeview in a second. This is a before and after of the sample site. So if you put on your Anaglyph glasses again, this is the one on the left is a stereo before we took the sample, before we even got close to the surface. The one on the right shows what happens after we took the sample. So you can see that all the major boulders are still in place, but that there is one boulder that got launched, and I outlined here, it's still hard to see. It got launched from the center. So the center is right in there. And this is before where you don't see the boulder in that circle. And this is after where you do see the boulder in that circle. We think that's the largest thing that got moved. It's a boulder almost a meter in diameter that our measly bottle of 3000 PSI nitrogen apparently launched like a rocket, and it moved a good like 10 meters. So we're talking about something almost a ton in mass that got moved by our bottle. So you can see Bennu is a really bizarre place because of the zero gravity. So I'm going to show the same thing in Freeview stereo. You can take your cardboard or your plate or whatever you're using to divide your eyes and prevent the right eye from seeing the left image and prevent the left eye from seeing the right image. You can put those in and then hopefully see the same thing in 3D. And I'm going to check the time here, make sure how I'm doing while you guys are doing that. I think we're good so far. I think this is the question and answer period, and that's good because this is like the next to the last slide. The last two slides I show in Freeview stereo are a little bit bigger. So this is before in Freeview stereo, and this is a little bit challenging. The images are bigger, which means they're wider apart. So unless you have wide eyes, it's going to be difficult for you to get your eye muscles to go all the way out to see this in 3D. But I thought I'd put it in anyway just to challenge you. And this is the same thing after we sampled. And I believe that's it. Yep, that's it. I'll take more questions now.
Great, thank you so much, Bashar. We'll wait for those questions to roll in. It was definitely a challenge to get my eyes to separate enough so that I could see that image overlapped.
Yeah, it's really funny, the idea of training your eye muscles, you know, but it's like any other muscle in your body.
We've got one more question coming in. What's next for Osiris-Rex?
Yeah, so we left the asteroid. We did our departure burn 6 days ago on Monday. So that was kind of a big to-do. A lot of us are rolling off the project now while the mission itself pushes on. So in 2.5 years, it comes back to Earth, September of 23. It's going to land. So the sequence of events is as follows. We boost directly toward the Earth with the combined spacecraft, and then we cut the tether that holds the sample return capsule to the spacecraft, and the sample return capsule starts its journey toward the Earth. Meanwhile, the main spacecraft diverts. So this happens about 4 hours out from the Earth, believe it or not. We cut it kind of close. The SRC, their sample return capsule, continues on to the Earth. And then once it enters the Earth's atmosphere, it slows abruptly. I mean, we're talking a lot of G's to decelerate this thing. And the heat shield takes the brunt of the force and the energy and keeps the sample hopefully from burning up. And once the thing slows enough, it deploys a drogue chute and then deploys the main chute. And the main chute allows it to drift slowly, relatively slowly, to the ground at the Utah Test and Training Range southwest of Salt Lake City. And where is the spacecraft now? The spacecraft is on the other side of the Earth's orbit from us, basically 15 light minutes away. What is that? That's like 200 million miles away, roughly. Why does it take so long to get back? Because you're trying to save fuel. So we could get back faster if we boosted with more fuel, but we wouldn't be able to have as nice a spacecraft because we'd have to spend more mass carrying fuel rather than instruments or nice avionics or good star trackers or a nice attitude control system with good gyros. What are the chances of the sample not making it back to Earth when it's ejected? Darn, that's a great question. Okay, the only way I can answer this, life is complex, guys, so I can't answer such a question theoretically, even though we've done probability calculations, just because it's a theoretical answer. We've flown 3 missions like this. 2 have made it back safely, 1 hasn't. It crushed the ground, but we were still able to salvage stuff from it. So I would put the chances of better than 2 and 3. What's the most exciting thing you've learned so far? That's a hard question to answer. I think we would have to say that the asteroid itself is partly a comet because it's ejecting material. Now it's called a rock comet, or it's joined the ranks of the population of rock comets. These are objects that we believe have burned up or used up all their surface volatiles, but still have enough oomph to eject stuff from their surface. So we observe these things in the solar system routinely from the ground, but we went to an object that we didn't expect to be like that, and it turned out to be part of that population. So it surprised us. So we all like to be surprised, especially pleasantly, and I think that would be the most exciting thing. Why did I want to be a scientist? Well, that's another hard question. I didn't start out to be a scientist. I guess I just floated into it. At a certain point, I had a choice, and I just looked at the kinds of things that I liked and that I was reading, and they all turned out to be somewhat related to physics or astronomy. So that I said, why fight it? I didn't think it was a field that I always thought required you to be really, really smart, and I didn't consider myself that smart. So I just, said, whatever, I'll be a mediocre one. And that's what I ended up being. What will happen to OREX after it sends the sample back? We will stay in solar orbit. We will have enough fuel to do, hopefully, another mission. They planned an extended mission, and the extended mission is a rather exciting one. We're proposing to NASA that we do it. NASA still has to make up its mind. The mission is to the asteroid Apophis. If you don't know who Apophis is, it's an asteroid that will come very, very close to the Earth in the year 2029, and it is one of the most hazardous asteroids out there. I should mention the Bennu itself is the 2nd most hazardous asteroid out there, but since the 1st most hazardous asteroid doesn't present itself with a hazardous opportunity for another 700 years, in terms of the next 200 years, Bennu is the most hazardous object out there. So we end up going, hopefully, to another hazardous place. Do you think there is water in your sample? There is bound water in the sample almost certainly because we detected it spectroscopically. Bound water, for those who do not know, is water that is contained within the crystalline structure of rock. So it's almost a part of the rock, as opposed to water that's just floating around as ice or liquid water. So we don't think there's any of that in the sample, but we think the water is bound. How do you find the asteroid in the sky and to determine its orbital path? You have to take pictures. We have to use light. The trick is to take pictures on different days and show the path curving, the longer the better, of the asteroid in the sky, and then you fit a mathematical function to it. These are all the same things that I've been talking about for almost half an hour now. Will Bennu run into the Earth? We don't think so. The chances of that are about 1 in 10,000 over the next 200 years.
Wow, that was quite the series of questions. Thank you so much for your time and your energy. This was a fantastic presentation, and I encourage anyone who's got more questions about OREX, to check out their website. It's asteroidmission.org. There's tons of great information and pictures on there too, including that great little video of the sample collection itself. Again, thank you so much, Dr. Rizk. And I also want to thank the Wyant College of Optical Sciences Student Optics Chapter for their demonstrations. Again, thank you to all of our presenting sponsors, Flandro, Optics Valley, and SBIE, along with our gold sponsors, the University of Arizona Bio5 Institute, Edmund Optics, Leonardo, PI, and VIAV. We really, really appreciate all the support. With that, I am going to hand it back over to Zach.
Olivia, thank you. And I have to ditto you. That was incredible presentations. I learned this fact recently, and I bring it up whenever I can because I don't think many people know it. And if we were in a physical room, I would want to see hands. I'm not asking for hands, but I'd be curious if you lined 10 people up in Tucson, how many would know that the U of A has been a part of every NASA planetary exploration mission since Apollo 11. We're talking 6 decades of space exploration that the University of Arizona has been a part of. So our legacy is so deep and rich in this space, no pun intended, but we don't often know about it. And just another really cool story that I'm glad that we got to tell. All right, it is my job now to send us to intermission. We will reconvene here at 3:40. Where we will learn how lasers are used in smartphones. So once again, thank you, Olivia. Thanks for hanging out with us all. Come on back in 9 minutes for much more here of our International Day of Light. We'll see you in a few.
Optics is big. In the Norwood lab, we use large solar troughs to collect solar energy and turn that into electricity or purify water.
Where optics can also be small, in Dr. Su's sensor lab, a wide range of particle sizes with radii from 2 to 100 nanometers can be detected using ultra-sensitive microtoroid optical resonators.
Optics is near. We use microscopes to get near objects to look at things that we can't see by eye, like the surface of this 2 on the 2002 written here on this penny in our microscope. In Dr. Ewan McLeod's lab, I work on lens-free microscopes. A lens-free microscope consists of a source and a sample placed very close to the sensor. We place our sample or object very near to the sensor to collect as much light from that object as possible. We then take what we've recorded on our sensor and plug it into the computer and use code to reconstruct our object instead of lenses. Here are images of clusters of 300 nanometer spherical particles.
Optics is invisible. Although it may not look like much, we can use wavelengths of light that are invisible to the human eye to do amazing things. In Dr. Barton's lab, I design and build imaging systems that will one day be used to detect ovarian cancer.
Optics is old. We can use infrared and X-ray imaging to learn more about the origin of antique artifacts. Working with researchers in the Netherlands, I used imaging to learn the past history and authenticate Renaissance paintings.
Optics is hot. Radiological imaging uses small amounts of radioactive material in the body to image gamma rays, which are detected by a special detector in combination with collimation optics to produce functional images of a living body. By working with Dr. Fernlid, I took part in making brain imagers which detect Parkinson's and Alzheimer's disease.
Optics is fast. Using extremely short laser pulses, this cool microscope called a multiphoton microscope can diagnose diseases like cancer much faster than traditional microscope techniques. And we have a bunch of them here at the College of Optical Sciences, including in my lab. These lasers use pulses on the order of femtoseconds, or 10 to the minus 15 seconds.
Optics is far. In my time in the optics department, I've had the opportunity to work on a project that is creating the instruments to study the interstellar medium. I've also had the opportunity to work on another project that is creating a trade study to see which camera will be best to study one of Jupiter's moons, Europa.
Optics makes your dreams come true. And let me tell you how optics made my dreams come true. I joined optics because I was obsessed with space. When I was 16, I looked through that telescope and saw the rings of Saturn for the first time and knew that I needed to make space exploration a part of my life. I joined optics specifically because everything we know about space is enabled by optics technology, from telescopes which look up into space to the cameras that go on the rovers and orbiters exploring planets in our solar system. And after getting my degree in optics, I was able to get my dream job. I'm recording this from Los Angeles, where I'm working for NASA's Jet Propulsion Laboratory, which, here's the proof, my ID, there's me, and there's NASA. It's an absolutely dream come true, and I share this with you because there isn't one of you watching this that could not achieve your dreams with a degree in optics. The College of Optics gives you all of the undergraduate research opportunities, internship opportunities that you would need to follow your dreams. So join optics and make your dreams come true.
Welcome to Arizona's Optics Valley. Optics and photonics are the science, engineering, and application of light used everywhere, every day. Arizona is home to world-class institutions and companies in optics, photonics, and astronomy. The industry has a $4 billion economic impact in Arizona. Optics Valley is the industry association that helps companies thrive through business acceleration, workforce development, and startup support, and connects Arizona companies to local and worldwide opportunities. The Optics Valley ecosystem supports strategic initiatives for innovation, growth, workforce development, and networking. Learn more about Optics Valley, where optics, photonics, and astronomy connect and grow.